Hey guys, so we are going to skip over section 6.7, integrals containing trig functions. These are some kind of crazy U substitution, excuse me, and trig identity problems. They're not tested on the AP exam, and I want to get everything done before winter break, so we're just going to skip over that lesson. So instead, you can head to 6.9. Integrands containing ax squared plus bx plus c, which are really quadratic formulas, and integrate using long division. So recall completing the square. We're going way back when, and completing the square is something that we use when we can't factor. So if I have x squared plus 6x plus 10, I know that it doesn't factor nicely into something that multiplies to be 10 but adds to be 6. So what we need to do instead, and I think this is what you did a lot of in algebra 2, is we said, okay, oops, I've got x squared plus 6x, and then we had to add some value here. I'm going to scooch the 10 over a little bit, and there's my equal 0. So the number that you added, if you recall, is half of the middle term, half the b term squared. So half of 6 is 3, 3 squared is 9. So we add 9 on the left, and I'm thinking you added 9 on the right as well. And then the left-hand side is now ready to factor. So this becomes x plus 3, which is the quantity x plus 3 squared. That's exactly what we want. We want a perfect square. And then the right-hand side is 9, something like that. Awesome, great, if we remember how to do this. Oh, you know what happened though? I made a mistake. What did I forget? Do you see it? I forgot this plus 10. So I believe then you subtracted it on the other side. There we go. And then maybe you said something like x minus 3 squared is equal to a -1. You find the square root. This one happens to not work out. You have an imaginary number. And then solve for x that way. We don't have to worry about imaginary numbers, and we're not necessarily solving quadratics like this, but we do have to complete the square. So what I have for you instead is an expression. So let's do this again. I have x squared plus 6x plus 10, but this time I don't have an equal sign. This is the version that I need you to remember how to do. And I don't know why I keep making extra lines. Let's try again. X squared plus 6x plus 10. So same idea, you want half the middle term, half of 6. So half of 6 is 3, 3 squared is 9. So I add 9, but then I also subtract 9. So the net change is 0. I'm really adding nothing if I add and subtract, but I am going to rearrange some pieces. So the way that I'll write this is x squared plus 6x. I'm going to bring the plus 9 over. And now my plus 10 and minus 9 stay on the end. So that is my double underline pieces there. So now the first part factors. I have x plus 3, a quantity squared, and then on the end a plus 1. And what's going to happen for some of these is they work out to be a nice antiderivative that we already know. I know that doesn't make sense yet, but it will. So if we jump right into example 1, find the integral of x squared plus 6x plus 10 in the bottom dx. Now, some of us are going to try to tell me that this is natural log of all of this. I wish it were that easy. You would have to have a U substitution problem. You would have to have a 2x somewhere in the numerator, and we don't have that. We could put the 2 in, we could take care of the 2, but you can't alter the x's. So it's not straight up natural log. So what we want to do is complete the square for this instead. And this conveniently is the problem we did just above. So this is dx over the quantity x plus 3 squared plus 1. And if you want to look up here, here it is. So now what can we do with this? Well, this is U substitution, where U is going to be x plus 3. du is going to be 1 dx. So when I rewrite this, this is du over u squared plus 1. You have to ask yourself, okay, where have you seen du over u squared plus 1? It's inverse trig. And in fact, it's inverse tangent. So this is inverse tangent of u plus c. And now I know u is x plus 3, so this is inverse tangent of x plus 3 plus c. And that is our solution. Okay, completing the square. Now, okay, so for example 2, I apologize that they're typed in here, but we're actually going to skip these. They don't work out quite as nicely as I thought they would, so we're going to skip right over those. But we will talk example 3. So example 3, I have dx over the square root of 2x minus x squared. So if I were to try this as a regular u substitution problem, it looks like that u would be equal to 2x minus x squared. And the derivative of that would be 2 minus 2x. Well, I don't have a 2 minus 2x in the numerator. I don't have anything that could be close to a 2 minus 2x. So regular u substitution does not work here. So we have to try something else. So let's see if we can rearrange this a little bit. I'm going to rewrite it with negative x squared in the front plus 2x. Now, before we do any kind of completing the square, we want to address this negative in the front. And I'm going to factor that inside the radical, but outside of the polynomial. I know that sounds weird. So negative x squared minus 2x. And I'm going to leave myself a lot of space here. Okay, so to complete the square, let's just see what happens. I want half of negative 2x. So half of negative 2x is negative 1 without the x. And then negative 1 squared is plus 1. So I add 1 inside the parentheses and I subtract 1. That's how it stays balanced. So now I'll take this piece and factor it. So we have dx over the square root. Here's my negative. This becomes x minus 1 quantity squared. And here's my minus 1 on the end. And don't forget, this negative is still in the front. Okay, so I'm going to take this negative and distribute it to both things inside of those brackets. So I have dx over the square root of negative x minus 1 squared plus 1. And if I switch the order of that, dx over the square root of 1 minus x minus 1 squared. Now, does this look a whole lot better than what we started with? No, not really. But we should be able to recognize that it belongs to one of those inverse trig functions. So if you remember, the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. And believe it or not, that's what we have. So we can say that u is equal to x minus 1, du is equal to 1 dx. So when we rewrite this, it's the integral of du over the square root of 1 minus u squared. And that's perfect for inverse sine. So this becomes the inverse sine of u plus c, inverse sine of x minus 1 plus c. And there is our antiderivative, our indefinite integral. All right, just double checking my work, making sure we're all good. All right, example 3 is great. Now, going way back to middle school, remember long division. So what does long division look like? Well, 624 over 5, we could write as 624 divided by 5. So then you ask yourself, okay, how many times does 5 go into 6? It goes once. 1 times 5 is 5. Subtract, I get a 12. 5 goes into 12 twice. 2 times 5 is 10. Subtract, I get a 24. 5 goes in there 4 times, so 4 times 5 is 20. Subtract, and I get a 4. And when we first started talking about these, we said, okay, remainder 4, right? Or then we could put the zeros and we did decimal places, or at some point, we had a fraction at the end. This is 1/24 and 4/5. And then we took that same idea and we applied it to rational expressions. So this one is x squared plus 1 over, or under, I guess I should say, x cubed plus 5x plus 10. So with this problem, we start with the highest powers. X squared goes into x cubed once. And then to get all the way to x cubed, you have to multiply by x. So x times x squared is x cubed. X times 1 is 1x. Then we change our signs. This is a minus, and this is a minus. X cubed minus x cubed is 0. And x times 1 is 1x. We did that. 5 minus 1 is 4x. Sorry, I got lost in my own subtraction here. And then we bring down the plus 10. So x squared into x, that's not going to work. The rest of this becomes a remainder. And this remainder is that fraction. So this is 4x plus 10 over x squared plus 1. Okay. So what does that mean for us with integrating? Well, if the power in the numerator is higher or equal to the power in the denominator, we can do some long division. So x minus 1 into x squared. Now, I'm going to fill in the other x's. I forgot to do that in our initial example. So I know that this is x. X times x is x squared. X times negative 1 is negative 1x. Subtract and add. I bring down a plus 1x plus 0. So this would be 1. 1 times x is 1x. 1 times negative 1 is negative 1. And so down comes a negative 1. So this is minus 1 over x minus 1. Now, the whole point of that long division is to separate it into smaller terms, and that's exactly what we've done. So now we're going to integrate x plus 1 minus 1 over x minus 1 dx. And we know that we can separate that to 3 separate integrals. I'm not going to write it like that, though. So the first term is x squared over 2 plus 1x minus, now this 1 over x minus 1, you can do a little u substitution. Du is going to be 1 dx. So I know this is 1 over u. The antiderivative of 1 over u is natural log. This is natural log of x minus 1, this whole thing, plus c. I kind of like these problems because it takes this ugly looking rational expression and turns it into 3 smaller or 4 smaller expressions that we can find the antiderivative of. Example 5 is a little bit longer, but let's try it out. Check your powers in the front. I've got x cubed over x squared, so this should work. X squared plus 1 over x cubed plus 5x plus 10. Make that a little shorter. So this will be x, multiply through. We've got x cubed plus x. I subtract those things, 4x plus 10. 4x plus 10 doesn't go in. This is the one that we had at the top, isn't it? Plus 4x plus 10 over x squared plus 1. Let's take a peek. Yep, exactly the one that was on the top of our page. So now we set up an integral. This would be the integral of x plus 4x plus 10 over x squared plus 1 dx. Now, in looking ahead a little bit, I see that the first term is a-okay. We can find the antiderivative of x. But in looking at this piece, this one's not so straightforward. I have x squared plus 1 in the bottom. So I want to ask myself, okay, what would u substitution be? u would be equal to x squared plus 1, and the derivative of that is 2x. But in the numerator, I have 4x plus 10. Sure, I could make the 2x and the 4x match up. I could manipulate it with a 2 and a 1/2, but that plus 10 is going to cause issues. So I can't use u substitution yet. I'm actually going to take the second piece and rewrite it as two separate fractions. Remember, we can split it apart at the plus sign. So this is 4x over x squared plus 1. And then it's 10 over x squared plus 1. Mrs. Charlie, you just took this problem that didn't look too terrible and you made it even longer. Yes, we did. But now it's three separate solvable problems instead of one that was not solvable before. So the first term, x, is going to be x squared over 2, or 1/2 x squared, you know that. The second term, now we can use that u substitution. So u is equal to x squared plus 1. The derivative of that is 2x dx. We solve for dx, and I have du over 2x. So pretend the dx is on the end. You can distribute that all the way through. 4x over 2x is going to leave me with a 2 in the numerator. And then that denominator instead of x squared plus 1 is u. And then the last term, 10 in the front and x squared plus 1 in the denominator. You want to think of this one as the integral 10 over x squared plus 1. And x squared plus 1 is inverse tangent. So this is plus 10 inverse tangent of x. I know this is a plus c. Now my notation here is terrible because I have x's and u's in the same problem. So I know that I need to replace that u in the denominator of the middle term. So this is x squared over 2 plus 2 over x squared plus 1 plus 10 inverse tangent of x plus c. So we're hitting all the integration skills in one problem there. All right, that's what I have for you. There was another way to divide, and I didn't put this in your notes because most of the time you guys remember that. If you have a linear factor in the denominator, meaning you have something to the first power, for example, 4 here, what was another way that you solved these? Perhaps it looked a little like this. Here's a 1. Here's a 0. Nope, it's not. It's a 1. See, I'm already getting this one wrong. Here's a 1, a 0, and a 0. Do you remember what this is? Remember synthetic division? Usually students are pretty good at this. So we take the opposite of this term down here, or this number. So instead of a -1, we're going to have a +1. The 1 in the front is your x squared term, and your x term, and then your constant. And if you go back to this, we bring down the 1. So 1 times 1 is 1. We add those together, we get a 1. And then 1 times 1 is 1. And hold on, I did this wrong. See, I'm never good at synthetic. Bring down the 1. 1 times 1 is 1. Subtract. No, I add. Plus 1. 1 times 1 is 1. Then I have 1 left over. That one's supposed to be a minus. All right, hold that thought. I don't have you with me to ask to see where my mistake is. Maybe you found it already. It's good to have a way to check your work. All right, so this is a +1. I'm not totally out there. And then these are always 1 power less. So this becomes your x, this is your constant, and then this term at the end is your remainder. So what it looks like here is 1x plus 1 plus 1 over x minus 1. Now, why don't these two match? Because I made a mistake the first time through. This is a plus, this is should be a plus over here. I made an error Here it is in my last step. I had 1 times -1, which is -1, and then I have to switch the signs. So this should be a plus. So this should be a plus. So this should be a plus, which is going to change this to a plus. All right. There you go. Don't do that. So what you're going to do for the rest of your time is to work on assignment number 6.9. I think that I'll do the same thing that I did yesterday. You can do the book problems. I think there are only 4 or 5 book problems on these type of division integration problems, or I will set up Delta Math and you can do the problems there. I do want you to try the AP practice problems, no matter if you do Delta Math or the book problems. So the AP practice multiple choice plus the book straight up practice or the Delta Math straight up practice. All right, keep emailing me with questions you have.